So next talk is Philippe Llewelyn from Matériaux Lab in southern France, and it's going to be the research director from the CNRS, and it's going to be talking about nanoporous materials for greenhouse gas mitigation.
Yeah. Bon, merci. Donc merci pour l'introduction, merci à Clément pour l'invitation, c'est super d'être ici. À partir de maintenant, je vais parler en anglais. So we've seen this morning quite a lot of lovely talks about different types of materials, and we've just heard some lovely talks also from Neil about some of his polymers and some of his punk crystals. Christian gave a talk this morning focusing on moths and water and how we could use some materials for energy applications. What I'd like to do is try and show you the experimental approaches on the lab scale anyway, how we could maybe evaluate materials to see whether they'd be of interest for example, CO2 capture. So in doing so, the first question is, why do we want to look at separations in general? Why would we want to look at CO2 capture in particular? So just to give you an idea, it costs 50 to 80% in terms of energy, and so in terms of money, to separate molecules. So around 10 to 15% of the world's energy is used for separations. And I took this publication from David Scholl and Ryan Lively, and I think the number you've got here is 98 quads, which is 100 exajoules. I've never heard of the word exa before, so you're way off the gigajoule scale. So it's a huge amount of energy just used for separations of molecules. A lot of these separations are thermal separations, so distillation, cryodistillation, and these are really, really expensive. So if we can use a porous material, for example, to separate these molecules, things become much, much less expensive because we don't have to worry about too much heating the system, as you would with distillation. So just to give you an idea, these are a few gas separations. So ethane from ethylene, so ethylene for polyethylene, polymers. You've also got propylene here for polypropylene. And you can see that the actual process cost is quite large for ethylene, and of that process cost, around 60% is just due to the separation. And you have the numbers here for ammonia, for methanol, and things like this. So huge amounts of money are just used for the separations. Coming back to Ryan and David's paper, they also picked out, so the actual, the title of the paper is 7 Separations to Change the World. And of these, you can see them all listed here. The ones with the red dots are ones that we've actually looked at in the lab over 10 or 20 years. The one I'm most interested in, what we're going to talk about today, is the greenhouse gases from dilute emissions. So what we're talking about is burning coal, burning natural gas, cement production, steel production, anything where you have to heat an awful lot. You're going to burn something to actually heat the system, and this is going to produce quite a lot of CO2. CO2 isn't just produced from these industries. There are many other sources of CO2, and this came out from Australia, saying that, for example, we've got other energy, we've got transport, of course, agriculture, and just waste. But what this graph shows us is around half of this are what we call point sources. And so they're places where we can put in a plant or an adder plant somewhere to capture the CO2. Fine. So how do we capture CO2? Well, there are several different means of doing this, coming from left to right. So cryogenics, so the air leak process, which is, you can see in black all the things that are good for. So it's good for pre-concentrated CO2. Gives us really pure gas and quite under pressure. Having the gas under pressure at the end of the process is of interest because we want to then transport maybe the CO2. And this is done at about 110 bar, so quite high pressures. The air leak process is at below minus 100 degrees Celsius, so it's really, really low temperature, which leaves the problem, gives us all the problems of process costs, the system itself, and of course real problems if there's any sort of contamination. And also we have a process with these sort of things. We've got to use valves. So opening and closing a valve at minus 100 degrees C is not that easy. So what most people have heard about is amine scrubbing. So taking a liquid, so maybe 10 or 15% of amine in water, so an amine solution, and this works quite well. We can capture almost 98% of CO2. It's a solution that's been known for years. So it's industrial ready. It's already been used on pilot scale and a lot of demonstration plants. But there's an excessive use of energy for regeneration and an awful loss of energy in terms of regeneration. Because if we have 10 to 15% of amine, it means we have an awful lot of water in the system, which we're heating up when we're regenerating. And we have to heat at over 100 degrees, 140 degrees. So we're just losing energy in heating up the water and cooling it down again. So, of course, if we're heating up amines in water, there can be corrosion problems with the amine itself, leading to toxic emissions. And the reactants age, and so the thing has to be changed or at least modified every now and again. Then there are two other solutions. So the last one is membranes, and this is the one that Neil would propose. Amine is very, very good. Different types of membranes, so the polymers, metal membranes, inorganic, and a whole series of different materials. So very, very good. In research in terms of mixed matrix membranes, so maybe taking one of Christian's MOFs and a bit of PIM, put them together and see what that gives us in terms of a decent different membrane. The problem with these systems at the moment is that the membranes are prone to degradation, to aging, and as soon as you get a hole in the membrane, you lose all of their properties. And this is what we've seen previously in the current research that we've looked at anyway, and we've got to that point. So problems of membrane lifetime, relatively expensive, that's a point of discussion, but maybe I would put it as our fourth or maybe really future approach. So the approach I talk about is adsorption. You take a material which is porous, you flow through the gas. One gas is maybe taken up a little bit more than the other, and it's a bit like chromatography basically. So just the smaller, maybe the less adsorbed gas will flow through the column and give us a way to purify or to separate the mixture. Loads of different materials are already used in adsorption processes. Zeolites, we've heard a lot about zeolites. Activated carbons, we've not heard a lot about activated carbons. And of course, all the work on different new materials, for example, Christian's MOS. The problem with adsorption at the moment is that sometimes we can have problems in terms of capacity. So we'd have to have materials with maybe better pore volume. Also the problem with contaminants. What happens if we have water in the system already? SOx, NOx, other things like this. And of course, again, depending on the type of process we're looking at, and if we look at the process in which we're playing around with pressure, and I'll come back to this, we have valves that open and close. And so from a process design point of view, we also have a problem in terms of the aging of the valves in the process itself. Which is why a membrane system would be quite nice, because you just open the system up, the gas flows through, and we just pick off on one side the retentate that we're interested in. So a nice little diagram in terms of relative energy consumption gives us distillation at 100%, and then other different processes that we could use for separations, so drying, evaporation, and we come down to adsorption of membranes, which are seem to an extent much more interesting in terms of energy consumption. If we come back to the four processes that I showed, so distillation would be our liquid process on the left-hand side. Amine scrubbing would be a bit like the drying process, maybe a little less energy intensive. But still, with respect to amines, we can see that things like adsorption would be use maybe 1/3 of the energy that we'd have for amine scrubbing, and membranes even less, at least on a theoretical point of view. So great. So I've said about absorption. We've heard words about absorption already today. What is it? So basically, you have any surface around the wall. The concentration of molecules close to this surface is is greater than in the bulk phase. So in any catalytic process, and this is what this cartoon is just showing, we're getting, for example, carbon monoxide sticking to the surface for a little while. It's reacting in this cartoon to make CO2. But this sticking part is the adsorption part. And this coming off part is what we'd call desorption. And it's a dynamic phenomenon. You have to remember this, and sometimes we forget this. So we can do simulation of absorption. We can model it quite simply using Leonard-Jones type descriptions to see the energy inside, for example, flat sheets, for example, of a carbon system. And we can get an idea that, for example, on the top animation, you will see that if the sheets are far apart, the energy, which is this straight, this line, it'll open up soon. Come on, open up. Okay, this is the whole system as we close slowly but surely. But you can see that at some point the two walls will come together, and when the two walls come together, the minimum potential energy that we see here will overlap, and we'll get quite strong interactions inside the pore. And this is why nanopores are interesting for absorption. And on the bottom is just some GCMC simulation of a pretty simple zeolite-like system, and argon, which sort of sits initially, the molecules will come in and sit on the walls, cover the walls, and then fill the rest of the porosity. Experimentally, what we can measure is an absorption isotherm, and this is what we have here. This is a pointer. Okay, so let's use this one. So we have an absorption isotherm here, so we have basically the uptake as a function of pressure, and what we have here in blue is CO2, and what we have in red here is methane on a moth, again, probably one of Christian's materials. What we can then do is the experimental points are the points. We can already theoretically model the behavior of the gases, and we can do this using different models, and this is just showing you one or two here, not of interest for the moment. What we can then do is calculate the initial slope. And we already heard someone talking about the Henry constant this morning. So basically, the greater the slope, the stronger the interaction, the higher the Henry constant. What is also of interest is the uptake at a given pressure. So this is what we have in green here. And we can compare the uptakes for example, our CO2 and our methane here. And if we do have two different isotherms with different gases, we can then start to predict something called selectivity, which is basically the way one material would maybe recover one gas with respect to the other. I don't want to go into details about this, but it's just an easy way to predict. So fine. So we have the models on the left-hand side. We have what we can do in the lab on the right-hand side. And we can then go to the pilot plant scale. So this is a pilot plant which I think is in the USA, so an ADA pilot plant, used for CO2 recovery, with an amine functionalized silica. Okay. So CO2 recovery using amine functionalized materials has already been tested. This is the pilot plant. The pilot was stopped because there were problems with the material. So that means that there's still an opening to look at new materials for CO2 capture. Okay, so different types of technologies. So one is working with pressure. We'll start at a lower working pressure, so the low end of the isotherm, go to a higher working pressure, somewhere higher in the isotherm. And what is interesting here is the working capacity, so the difference in uptake between our lower working pressure and our higher working pressure. And if we have a good separation, CO2 nitrogen, for example, here, we'll have a bigger working capacity for gas 1, CO2, and a much lower working capacity for gas 2, which would be hopefully our nitrogen. And basically all we do is go up in pressure and down in pressure and play around. Going up and down in pressure, I've learned recently, costs a lot of money. However, in any process, there's often waste heat that can be recovered for regeneration. So a lot of people, are, at least on the process scale, are maybe more interested in looking at things like temperature swing adsorption. So adsorption is an exothermic process. We heard that before. So as we go up in temperature, we adsorb less. So all we have to do is play around with temperature, so an upper working temperature and a lower working temperature. The working capacity is just the difference between the uptakes at these two temperatures. And design a system that can adsorb at lower temperature, find waste heat to do the regeneration, to recover to regenerate the system at a higher temperature. Two main processes. There are other little processes, other processes that we can look at, but just there are variations on these themes. An awful lot of work, and this is what I'm learning at the moment, an awful lot of work is set on trying to optimize these processes and also looking at really clever process designs. So, for example, I'm showing columns here, but we could imagine the thermal swing as a wheel. So you have one bit where you have the adsorption, the rest for the desorption. Or we can have, for example, hollow fibers. So our adsorbent material is on the outside of the fiber, but on the inside is our cooling or our heating, for example, water, to go through the temperature swing. So a lot of clever ideas in how to modify these general technologies to make them maybe more efficient. Okay, so this is where we were here. So the question is, what is the adsorbent material we want to use and what we want to put in them? So we've heard about zeolites, we've heard about MOFs. The first thing we should maybe start with is active carbons. They're cheap, the oldest known adsorbent, used since the Egyptian times. They're pretty amorphous, but it is really quite easy to engineer the pore size. Generally hydrophobic, often have quite high pore volume, and generally quite cheap. Okay. And the image you have on the right-hand side is just an idea of where we can put in argon molecules into one type of activated carbon. So I'm not going to talk more about zeolites, but Svetlana talked about zeolites, and they're over 230 different structures. We can engineer the T atoms, so that the metals we put inside. We can have a specific pore size, and we can play with other things, for example, with cations. So I think Svetlana talked about putting in cesium, for example, to have trapdoor effects. And finally, so Christian gave a really nice talk about metal organic frameworks. Thousands of different structures, a huge range of chemistries, so an awful lot to choose from. And this is maybe one of the problems with MOFs, is there are maybe too many materials to choose from. Okay. Structural flexibility. But the other thing, even though Svetlana talked about structural flexibility, it's not the same as you have in MOFs. You can have, for example, Christian's MIL53 material, which opens and closes like this. Or even materials in which the organic linker can move like this, so open and close. So a lot of things to play with. And our problem on the lab scale is to go through this. How can we get milligram or less than gram quantity materials and test them to find out whether they could be of interest for the pilot scale that I'm showing down here on the left-hand side? So things we can look at: uptakes, interaction strength, separation power. There's an awful lot of work being done in the literature, so we should maybe go back to data mining, and I'll try and show you what we're doing at the moment on this. Then the question of how to choose the best material. And then finally, what maybe some people don't really look at as much, and we are starting to do a little bit more on the lab scale, are the effect of contaminants, and especially water. Okay, so what we do in the lab. So in the lab, we've built our own bits of apparatus to work at room temperature. We have 2 pieces of apparatus which can work each with 6 samples each, so we can work at 12 samples at a time. What we designed is a system in which we can use less than 100 milligrams a sample to get a pretty good idea of what the isotherm looks like, and that's pretty good. And we've got a program set up that we can look at isotherms up to pretty decent pressure at different temperatures, but we stay mostly at 25 to 30 degrees. But also we can change the gases, and we can look at 4 different gases sequentially, which is really nice. And it's possible to cycle, so we can do a lot of things already with quite a simple system that we built in the lab. So on the right-hand side, you have 2 different series of isotherms with different metal organic frameworks. So Christian's MIL 100, made with different metals, and you can see the different metals or the different materials we had have different uptakes. And we can see for the vanadium sample, we had 2 different samples, one which is maybe of a little bit lower quality than the other. So it's a good way to screen through materials. On the right-hand side, you have some CAU10 materials, so these from Kiel. And here, what they've done is looked at different functions, so functionalizing the organic part. And again, we can just see the difference in CO2 uptakes. So that's quite nice and quite easy to do. The problem here is data management. So just to give you an idea, we had a student come over for a month. He said he wanted to come for a month. I asked him how many samples he had. He said he had 6. So I said, fine. When he arrived on the plane and I picked him up at the airport, he had 36 samples. So basically, we said, okay, he's going to use this for a month. He used it for a month, day and night, over the whole month, the weekends included. came away with 350 isotherms, different gases, different materials, and spent, I think, the rest of his PhD just trying to go through these isotherms and get ideas. So our problem now is data management. So what we're doing with Paul, so Paul has finished his PhD and is just about to leave us to go off to do a postdoc, is to go to the NIST database. So the NIST database is a database of isotherms. So over 2 or 3 years, they have gone through a load of different literature data and got maybe around 35,000 isotherm points. So they've got 35,000 isotherms. Paul found a way to download them all. So contacted NIST and downloaded them. And what we're trying to do is find ways to go through this and look at all of these different points. So we have on the left-hand side the uptakes at, I think, 0.8 bar for nitrogen with respect to CO2. On the right-hand side, our initial interaction strengths, so the Henry constant. So if I'm going to leave this, oh God, I'm going to have to go over here somewhere. Go to here. Okay, I'm going to have to do something really weird. Sorry. I'm on the wrong side. Here we go. Take him. Come over here. So this is what we've got. I don't know whether I can make this the right size. Okay, doesn't matter. So this is what we got. So this is just for outcomes. Sorry. Joys of computer. So what we've got here is we can pick on the point. So this is mil 47. So find the mil 47 point in terms of uptake, and then what is difficult to do on this scale anyway is to see what happens on the right hand side. You have to believe me that if we go from one graph to the other, we can see if we have mil 47 on one side in terms of uptakes, what does that mean? And on the right hand side in terms of Henry constants, how does it fit out? So we can find materials that maybe have a really good ratio in terms of Henry constant, but really sort of average in terms of uptakes. So that's one way already that we're trying to do to look at this data mining. That's unfortunate, it didn't work as good as I'd hoped. Doesn't matter. So here we are. So the idea is that we can go from left-hand side to the right-hand side. So maybe some of the materials we have on the right-hand side seem to have really good Henry constants, for example, for CO2 with respect to nitrogen. So basically, we want materials in the bottom right-hand corner in each of these two. So for things, we can come back to this later, but there are materials that look really much of interest. And 2 or 3 of them are actually Christians, which is unfortunate. Well, they're really fortunate for him, but unfortunate for the people who decry some of Christian's work. So what we can then do is calorimetry. Calorimetry is a speciality of our group in Marseille. It's been a speciality for years. And we can measure directly the energies of interaction. For example, this is CO2 and methane on a mil 100 and a mil 101, so some of these big, large cage MOFs. We can get from this either the difference in initial uptakes, so the difference between at the top here, the CO2 and the methane, or at the bottom, we can just integrate over a pressure range, over a pressure range, the heat that is given out. The heat is an important parameter. It's a huge parameter in terms of process. Any small amount of heat in a process has to be managed at some point. So it's something that we have to take into account. So this is what we did with Virginie, for example. Look at things like working capacity, so the amount absorbed over a different pressure range. And this is for CO2, nitrogen at the post-combustion conditions. So these are a whole series of different MOFs. On the right-hand side, we're comparing with the Takeda 5A, which is a carbon. And we can see that we can sort of relate the best uptakes with a sort of variation in pore size, for example, or a surface area, but I think they're both more or less related. We can do the same thing in terms of energy. So we can compare, again, the Takedas on the right-hand side with different MOFs. We would want something with maybe something like a moderate energy. So this is the difference between the CO2 and the nitrogen. And again, we can relate the smaller the pores, the bigger this difference. Finally, we can look at selectivity, so the way that one material would separate CO2 from nitrogen. And we can get these different values coming off here. The problem now is we've got these 3 different key parameters. We don't know which material to choose. You know, do we want one with a really high working capacity, but we're prepared to have poor selectivity, or we'd want to, how do we do this? So what we did with a former PhD student is just come up with a formula, which is up here on the right-hand side. We've taken the working capacity, we've multiplied it by the selectivity, and we divided it by the energy, because the heat that we've measured, or the enthalpy that we've measured, we want to be as low as possible. What is not on this formula here is that we've put in exponents as well, which means that, for example, if you want something which has a really big working capacity, we can have this squared, for example. And this helps us choose a bit more. So we can already see here that we've got maybe 4 or 5 candidate materials that we can take forward for testing. Of these, 1 ZIF, 2 ZIFs, and a small pore, 2 quite small pore MOFs, at least for this system. So very quickly, some separations that we're interested in. So these are another series of experiments. So this is CO2 from methane. Sodium X seems the best, but you'll find later that things with zeolites have problems with water, for example. Other small pore materials, so both of these seem to show that MIL91 is of interest. And then we go to other separations, for example, CO2 from nitrogen, or propane from propylene. We'd like to have maybe free metal sites. So these are the materials that come out. So fine. So we've picked out a material. We found that it has good working capacities or whatever. The first problem after that is someone's going to say, okay, in my process I have contaminants, and the flue gas is wet. There's water in there. So what we've done is set up a really simple system in that we've looked at the CO2 uptake at 0.2 bar, so around a little bit below atmospheric. So the sort of pressure range that would be used in applications, in a wet system and in a dry system. So if we look on the left-hand side, we have 1 or 2 zeolites, and we can see in green a really good CO2 uptake. But in the presence of water, the uptake capacity decreases immensely. So the blue is in the presence of water. So then on the right-hand side, we have a lot of carbons, and in between, we have a whole series of different MOFs. And there you have the names here. So we've picked out a whole series of MOFs which could be of interest for CO2 uptake in the presence of humidity. What other people have done is taken this further and looked at the CO2 uptake and the selectivity of CO2 nitrogen in the dry state, so the green lines, in the wet state, blue lines, but also after treatment in SOx and NOx to see whether the materials degrade. And so that is also of interest in a way of screening. There is also high-throughput experiments to look at other contaminants. Okay. So that's great. That's all the experiments. But you have people from molecular simulation to say, okay, why not use computer-aided approaches? And there's one group that have made 130,000 hypothetical MOFs and said, okay. And they've looked at this, for example, for methane storage or for hydrogen storage, something quite simple. What they did, or one of the studies that they did, was to compare with another approach based on QSPR, so structure property relationships. So both of them more or less theoretical approaches, but they give different results, different answers in terms of methane storage. So of these, so there are 2 points. First of all, if you talk to Christian and you say, okay, we found this MOF that's really of interest, a lot of the MOFs that they found of interest were actually really difficult or probably impossible to synthesize. So there needs at least some sort of rationalization in terms of someone who's specialist in synthesis. And then there's also the incoherence between the approaches, which means some sort of validation from experimental data. Just to take this further, so we can even look at theoretical databases. So the hypothetical MOF database with of 130,000 entrances, and the core database, which has already been slimmed down. You can also see that there are incoherences. On the right-hand side, you have the comparison with literature. We can see that there's a problem in comparison with literature. Okay, we don't have a straight line. So this is where we are. You have people from molecular modeling say we should use molecular modeling. People from experiments say we should use experiments. And this is basically, really quickly, what we have done and we've set up in the lab in collaboration with Christian, and we've already heard about Guillaume Morin. Try and use a 3-step approach. Look at single gas experiments, look at the humidity, and then look at the effect of contaminants before going on to our selection strategy. And then when we've selected, maybe we can then go to pelletization and then look at breakthrough and pilot scale testing. We then go from small amounts of materials to larger amounts of materials, from powders to pellet materials. In terms of molecular modeling, we're at this point where single gas experiments, no problem. Introducing the effect of humidity is now not a problem, but going further on in terms of looking at other contaminants, especially SOx and NOx, becomes problematic. So really quickly, last two slides. Our current research strategy with Christian, Guillaume, and Jean-Cinq, for example, is to actually just look at the small scale at the moment. Talk with people from Synthesis, talk with Guillaume, maybe start with a system, with a structure which we think is okay, play around with functions and do a little bit of molecular modeling to try and hone into a material of interest. And then go to the kilogram scale and process design. What would be more of interest, and I've talked about process, is to start with process design, talk to people from molecular modeling, see whether there's a compromise between the two, knowing that now we're in a case, or there are one or two groups in the world in terms of molecular modeling which actually make something quite viable, actually use screening techniques based on experimental data as well. So that may be a way forward. Start with them without talking to the experimentalists. Then make sure that we validate some of the structures that we found out in terms of isotherms, etc., but especially in terms of stability and contaminants. Then worry about synthesis, upscale, and shaping. After that validation step, come back to the process design. And so that's really challenging, because talking to people from process design and molecular modeling, they're two different scales, hugely different scales. Bringing them together in the same room is not going to be easy. I've been lucky to be contacted by Total. So basically, after the COP21 agreement in Paris, what they decided is to put aside a huge amount of money to look at the whole carbon problem. And part of this is going to be hopefully set up to look at this type of project. So start with the best in process design, some really good people in molecular modeling, before then finding out, okay, these could be the best materials, polymers, MOFs, silicas, and then talk to the synthesis people to do the next part of the work. So when they said I was going to Total, this is what I'm going to be doing. So with that, thank you very much for your attention. These are some of the people that have done some of the work.